Hello everyone, my name's Iman. Welcome back to my YouTube channel. Today we're going to be tackling a practice problem set that relates to our lecture on solutions. Let's go ahead and get started with problem number 1. Problem number 1 says an aqueous solution was prepared by mixing 70 grams of an unknown non-dissociating solute into 100 grams of water. The solution has a boiling point of 101 degrees Celsius. What is the molar mass of the solute? We're also given the Kb value for water. Okay, so this problem asks us to determine the molar mass of an unknown solute based on the change in boiling point of the solution. So what we're given here is the mass of the solute, 70 grams. We're given the mass of the solvent, 100 grams. We're also given the boiling point elevation, delta Tb. We're told that the solution boils at 101 degrees Celsius, and the boiling point of just pure water is 100. So we can take the difference between 101 degrees Celsius and 100 degrees Celsius to get a difference of 1 degree Celsius. So the boiling point elevation is 1 degree Celsius. We're also given the proportionality constant, Kb for water, which is equal to 0.512 Kelvin times kilograms per mole. And the last thing that we're given here is also the Van Hoff factor for the solute. It's going to be equal to 1 because the molecule does not dissociate into smaller components. We're given that in the question stem where they say this unknown non-dissociating solute. So with all of this information, here is our game plan. We're trying to figure out the molar mass of the solute. Molar mass is grams per mole. We have the grams of the solute, 70 grams of our solute. We need to figure out the moles of the solute so then we can take grams per mole and figure out our molar mass. How are we going to get there with the information we're given? The first thing that we're going to do is use our boiling point elevation expression. All right, delta Tb is equal to I Kb m, where I is our Van Hoff factor, Kb, this is our proportionality constant, and m is molality. Now we can rearrange this equation to actually solve for molality since we're given all of the other variables. In this case, it's going to be that delta Tb over I Kb is equal to molality. Now we know all of these quantities, so we can go ahead and plug them in. Delta Tb is 1 over I, which is 1, and Kb is 0.512. All right, so we can approximate this as 1 over 0.5. This is equal to 2. So the molality is equal to 2. Beautiful. Now this is getting us one step closer. We know, again, that we have 70 grams of this solute. We need to figure out the moles, and we can actually get that from molality. What is the definition for molality? Molality is equal to moles of solute over kilogram of solvent. We know the molality, we just calculated it. We know the kilograms of solvent, actually we know it in grams, but that's an easy conversion to kilograms. We have 100 grams of water. This is equal to 0.1 kilograms of water. So then what we have to do is take our definition for molality and rearrange it to solve for moles of solute. Moles of solute is going to equal molality multiplied by kilograms of solvent. So this is going to equal 2 multiplied by 0.1. And this is going to give us 0.2 moles. Now we have everything to figure out the molar mass of our solute. We have 70 grams divided by 0.2 mole. So 70 grams divided by 0.2 mole is equal to 350 grams per mole. The closest answer to this is going to be answer choice A. So the correct answer for problem 1 is A. Beautiful. Let's move on to problem 2. Problem 2 says, which phases of solvent and solute can form a solution? Statement 1 says solid solvent, gaseous solute. Statement 2 says solid solvent, solid solute. And statement 3 says gaseous solvent, gaseous solute. Now, this problem is asking us which of these combinations of phases of solvent and solute can form a solution. To solve this problem, we need to understand the basic principles of solution chemistry, where a solution is defined as a homogeneous mixture of two or more substances. Now let's go over each statement. Statement 1 says solid solvent, gaseous solute. Now this is possible for a solution. An example of this could be hydrogen gas being absorbed into palladium. This type of solution is possible, and it forms what is known as a solid gas solution. So this is correct. What about statement 2? Statement 2 says solid solvent, solid solute. So in this scenario, both the solvent and the solute are solids. Now an example would be alloys such as brass, which is a mixture of copper and zinc. This type of solution is also possible, and it's known as a solid-solid solution. So statement 2 is also correct. What about statement 3? Gaseous solvent, gaseous solute. So here both the solvent and solute are gases. Now the most common example of this is air. Air is a mixture of nitrogen, oxygen, and other gases. So this type of solution is also possible, and it's known as a gas-gas solution. All three choices can make a solution as long as the two components create a mixture that is of uniform appearance. And so the correct answer for problem 2 is going to be D. Statements 1, 2, and 3 are all correct. Let's tackle example 3 now. Problem 3 says two organic liquids pictured in the figure below are combined to form a solution. Based on their structures, will the solution closely obey Raoult's law? A says yes, the liquids differ due to the additional methyl group on toluene and therefore will not deviate from Raoult's law. B says yes, the liquids are very similar and therefore will not deviate from Raoult's law. C says no, the liquids differ due to the additional methyl group on toluene and therefore will deviate from Raoult's law. And D says no, the liquids both contain benzene rings which will interact with each other and cause deviations from Raoult's law. So this problem, it's asking us whether a solution of these two organic liquids, benzene and toluene, will closely obey Raoult's law based on their structures. Now, Raoult's law states that the partial vapor pressure of each component in an ideal solution is going to be directly proportional to its mole fraction in the solution. Now, an ideal solution obeys Raoult's law under two conditions. The first one is that the intermolecular forces between the molecules of different components are similar to those between the molecules of each component. The second condition is that the components have very similar molecular sizes and structures. So let's take a look at benzene and toluene. Benzene is a simple aromatic hydrocarbon with the formula C6H6. It consists of 6 carbon rings with alternating double bonds. Toluene is very similar to benzene, but it has a methyl group that's attached to one of the carbons in the ring, giving it the formula C7H8. Now, the primary difference between benzene and toluene is the presence of that methyl group in toluene. This methyl group adds slightly to the molecular size, and it introduces a minor difference in intermolecular forces due to the slight polarity of the methyl group. But since benzene and toluene are structurally very similar, they're both aromatic hydrocarbons, the intermolecular forces between benzene and toluene molecules is going to be really similar to those between benzene and benzene molecules and between toluene and toluene molecules. This means that when benzene and toluene are mixed, their interactions will be quite similar to their pure states, making the solution behave ideally. Considering all that, the correct answer to the problem is going to be B. Will the solutions closely obey Raoult's law? Yes, the liquids are very similar and therefore will not deviate from Raoult's law. Remember, liquids are very similar in structure here, so they're likely to obey Raoult's law. They are both organic aromatic hydrocarbons. They have very similar properties. They're both nonpolar and almost exactly the same size. So answer choice B makes the most sense. Awesome, let's tackle problem 4 next. Problem 4 asks, which of the following explanations best describes the mechanism by which solute particles affect the melting point of ice? A says melting point is elevated because the kinetic energy of the substance increases. B says melting point is elevated because the kinetic energy of the substance decreases. C says melting point is depressed because solute particles interfere with lattice formation. And D says melting point is depressed because solute particles enhance lattice formation. The key here is to remember that when a solute is added to a solvent, the resulting solution often exhibits colligative properties. One of those properties is freezing point depression, which is the lowering of the freezing point of a solvent due to the presence of a solute. Freezing point depression occurs because the solute particles actually interfere with the formation of the solid structure of the solvent, and that makes it more difficult for the solvent molecules to organize into a solid. Now, this interference requires the solution to be cooled to a lower temperature to achieve the same level of solid formation. Now, the key mechanism here for this problem is the interference of solute particles with the solvent's lattice formation. So when solute particles are present in water, they disrupt the hydrogen bonding network that's necessary for ice to form. And this disruption requires a lower temperature to overcome the presence of the solute particles and to form solid ice. So then with that statement being made, we can quickly eliminate A and B because it's telling us that melting point is elevated, and we just said that melting point is depressed. You need to go to a lower temperature to overcome the presence of the solute particles and to form solid ice. And again, this is because solute particles interfere with lattice formation, and that makes the correct answer choice C. 4 is C. 5 says, the process of formation of a salt solution can be better understood by breaking the process into 3 steps. Step 1, breaking the solute into its individual components. Step 2, making room for the solute in the solvent by overcoming intermolecular forces in the solvent. Step 3, allowing solute-solvent interactions to occur to form the solution. Which of the following correctly lists the enthalpy changes for these 3 steps respectively? So we need to determine whether each step is endothermic, absorbs heat, or exothermic, releases heat. Let's look at step 1, breaking the solute into its individual components. So this step involves breaking the ionic bonds in the solid salt, the solute, to separate it into its individual ions. Breaking bonds requires energy input. Therefore, this first step, is endothermic. Let's look at step 2, making room for the solute in the solvent. So this step involves separating the solvent molecules to create space for the solute ions. Overcoming the intermolecular forces between the solvent molecules also requires energy input. So this step is also endothermic. Then step 3, allowing solute-solvent interactions to occur. So this step involves the solute ions interacting with the solvent molecules and forming these new interactions. Forming new interactions releases energy. Therefore, this step is actually exothermic. So based on this analysis, the enthalpy changes for the 3 steps are endothermic, endothermic, exothermic, and that best matches answer choice D. 5 is D. Let's move on to problem 6. Problem 6 reads, the entropy change when a solution forms can be expressed by the term delta S of solution. When water molecules become ordered around an ion as it dissolves, the ordering would be expected to make a negative contribution to delta S. An ion that has more charge density will have a greater hydration effect or ordering of water molecules. In an experiment, an equal molar amount of each of the following soluble compounds is dissolved in its own test tube containing 100 milliliters of water. Which will have the most negative contribution to delta S of solution? Assume that the charge density of each ion is equal to its actual charge. Okay, and answer choice A is potassium chloride, B is cesium iodide, C is beryllium fluoride, and D is sodium chloride. Now, let me reiterate, when water molecules become ordered around an ion as it dissolves, this ordering results in a decrease in entropy, making a negative contribution to delta S of solution. So an ion with a higher charge density will have a greater hydration effect, leading to more ordering of water molecules and a more negative delta S of solution. Now here we want to assume that the charge density of each ion is equal to its actual charge. So let's examine the charge of each ion in the given compounds. Starting off with A, we have potassium chloride. It has potassium cations with a +1 charge, chloride anions with a -1 charge. B is cesium iodide. Cesium has a +1 charge and iodide has a -1 charge. C is beryllium fluoride. Beryllium has a 2+ charge and fluoride has a -1 charge. And our last answer choice, sodium chloride. Sodium has a +1 charge and chloride has a -1 charge. So among the given compounds, beryllium has the highest cation charge. It has a +2 charge. This means that it's going to have the strongest electrostatic interactions with water molecules, leading to the greatest ordering of water molecules around it, resulting in the most negative contribution to delta S of solution, especially considering that all of these compounds, their anions all have a -1 charge. And then looking at the cations, beryllium is the only one that has a +2 charge, while the other three all have a +1 charge. And considering that the question tells us to assume that the charge density of each ion is equal to its actual charge, the correct answer for problem 6 is answer choice C. Let's move on to problem 7. Problem 7 says, when ammonia is used as a solvent, it can form complex ions. For example, dissolving silver chloride in ammonia will result in this complex ion. What effect would the formation of complex ions have on the solubility of a compound like silver chloride in ammonia? A says the solubility of silver chloride will increase because complex ion formation will cause more ions to exist in solution, which interact with silver chloride to cause it to dissociate. B says the solubility of silver chloride will increase because complex ion formation will consume silver cations and cause the equilibrium to shift away from solid silver chloride. C says the solubility of silver chloride will decrease because silver cations are in complexes and the silver ion that are not complexed will dissociate with chloride to form solid silver chloride. And D says the solubility of silver chloride will decrease because complex ion formation will consume the silver ions and cause the equilibrium to shift towards the solid silver chloride. Now, when a compound like silver chloride dissolves in ammonia, the silver ions, they can form a complex ion with the ammonia. Now, the formation of this complex ion, it can affect the solubility of silver chloride by shifting the equilibrium of this dissolution reaction. Le Chatelier's principle, it states that if a change is imposed on a system at equilibrium, the system's going to adjust to counteract that change and then reestablish equilibrium. In this case, the formation of the complex ion consumes silver ions. So let's evaluate each of these options based off of that information. A says that the solubility of silver chloride is going to increase because complex ion formation will cause more ions to exist in solution, which interact with silver chloride to cause it to dissociate. Now, this option suggests that more ions in solution will interact with silver chloride to cause it to dissociate. The key mechanism is actually the consumption of silver ions and not the interaction with silver chloride. So this option is incorrect. Answer choice B says the solubility of silver chloride will increase because complex ion formation will consume silver ions and cause the equilibrium to shift away from solid silver chloride. This option correctly states that the solubility of silver chloride will increase because complex ion formation is going to consume silver ions, and that's going to cause the equilibrium to shift away from solid silver chloride. So this answer choice is actually correct. But let's work through C and D anyway. C says the solubility of silver chloride will decrease because silver ions are in complexes, and the silver ions that are not complex will associate with chloride to form solid silver chloride. Now, this option, this is suggesting that solubility decreases because silver ions are in complexes. The formation of the complex actually increases solubility because it's removing silver ions from the solution, which to re-equilibrate is going to cause silver chloride to dissociate. And so answer choice C is incorrect. Answer choice D says the solubility of silver chloride will decrease because complex ion formation will consume silver ions, and this causes the equilibrium to shift toward the solid silver chloride. Now, this option is incorrect because it states that the solubility will decrease due to the consumption of silver ions, and that's going to cause the equilibrium to shift towards forming silver chloride, when actually the equilibrium actually shifts to dissolve more silver chloride. And so option D is also incorrect. The correct answer to problem 7 is B. Moving on to problem 8. Problem 8 says 100 grams of sucrose are dissolved in a cup of hot water at 80 degrees Celsius. The cup of water contains 300 milliliters of water. What is the percent composition by mass of the sugar in the resulting solution? Note that sucrose is C12H22O11 and the density of water at 80 degrees Celsius is 0.975 grams per milliliter. Now, the mass percent of a solute, this is equal to the mass of the solute divided by the mass of the solution multiplied by 100%. Now, we're interested in the percent composition by mass of the sugar, sucrose. So that means our expression is going to be the mass of sucrose, which is 100 grams, divided by the total mass of the solution. This is going to be 100 grams of sucrose plus the mass of water. Now, we're not directly given the mass of water, but we can figure it out with the information we are given. We have the volume of water, 300 milliliters, and the density of water. Now, density is equal to mass over volume. If we're curious in solving for mass, we can rearrange this expression to get that mass is equal to density multiplied by volume. Now, we have both of these quantities, so we can plug them in to solve for mass. The density is 0.975 grams per milliliter, and this is multiplied by the volume, which is 300 milliliters. Now, when we multiply this out, we get 293 grams. Now, we can take this quantity and plug it back into our expression. We have 100 grams of sucrose in the numerator, and then we have 100 grams of sucrose plus 293 grams of water, and that gets us 100 over 393 multiplied by 100%. This is going to give us 25.5%, which best aligns with answer choice B. So the answer to example 8 is answer choice B. Let's tackle 9. Problem 9 says which of the following combinations of liquids would be expected to have a vapor pressure higher than the vapor pressure that would be predicted by Raoult's law. To solve this, we need to understand how Raoult's law works and how deviations from it occur. And this involves us talking about positive deviation and negative deviation. Positive deviation occurs when the interactions between the different molecules are weaker than the interactions between the same molecules, and this leads to an increase in vapor pressure. In other words, whenever the solute-solvent interactions are weaker than the solute-solute and the solvent-solvent interactions, then this leads to an increase in vapor pressure. What about negative deviation? Negative deviation occurs when the interactions between the different molecules are stronger than the interactions between the same molecules, and this leads to a decrease in vapor pressure. So in other words, whenever the solute-solvent interactions are stronger than the solute-solute and solvent-solvent interactions, then this results in a decrease in vapor pressure. Now let's evaluate each combination based on the types of interactions and figure out which one is the correct answer. A says ethanol and hexane. Ethanol can form hydrogen bonds due to the OH alcohol group it has. Hexane, this is a hydrocarbon. It is nonpolar. It does not form hydrogen bonds. The interaction between ethanol, which is polar, and hexane, which is nonpolar, will be weaker than the interactions within ethanol and within hexane. And so this is going to lead to a positive deviation. This is going to lead to an increase in vapor pressure. This matches what our question is asking. It's actually the correct answer, but I still want to work through the other answer choices. B says acetone and water. Acetone has a polar carbonyl group, and it can engage in dipole-dipole interactions. Water can form hydrogen bonds, which is a type of dipole-dipole interaction. So the interaction between acetone and water, it's going to involve hydrogen bonding and dipole-dipole interactions. These interactions are relatively strong, and this could lead to actually negative deviation, which is not what this problem is asking. So answer choice B is not correct. C says isopropanol and methanol. Both of these can form hydrogen bonds, and so the interaction between them is going to be pretty similar, and that's going to lead to minimal deviations from Raoult's law. So C is also not the correct answer. D says nitric acid and water. Nitric acid is highly polar and it can form hydrogen bonds. Water can also form hydrogen bonds. And so the interaction between nitric acid and water, this is going to involve strong hydrogen bonding. This is likely going to lead to negative deviation. So again, this is not what the problem is asking. So it's not the correct answer. Between our analysis, of all 4 of these options, ethanol and hexane are going to exhibit weaker interactions between each other compared to their pure states. This is going to lead to a positive deviation and a higher vapor pressure than predicted by Raoult's law. So the correct answer for problem 9 is going to be A. Let's go ahead and move into problem 10. Problem 10 says the salt of potassium chloride is dissolved in a beaker. To an observer holding the beaker, the solution begins to feel colder as the potassium chloride dissolves. From this observation, one can conclude that blank. A says that the delta S is large enough to overcome the unfavorable delta H. B says potassium chloride is mostly insoluble in water. C says delta S must be negative when potassium chloride dissolves, and D says boiling point depression will occur in this solution. Now, dissolution is governed by enthalpy and entropy, and they're related by this equation. Delta G is equal to delta H minus T delta S. Now, The cooling of the solution indicates that heat is used up in this bond-breaking reaction. So in other words, dissolution is endothermic and delta H is positive. Now this reaction is occurring spontaneously, so delta G is negative. The only way that a positive delta H can result in a negative delta G is if entropy, delta S, is large and positive. And that makes the correct answer choice A. Now, B is incorrect because it is clearly stated that potassium chloride dissolves. Also, if you remember your solubility rules, all salts of group 1 metals are soluble. So B is incorrect. C is also incorrect because delta S must be positive in order for potassium chloride to dissolve. And then D is incorrect because solute dissolution would cause the boiling point to elevate, not depress. And so that answer choice is also incorrect. It is also not a piece of evidence that could be found simply by observing the beaker's temperature change. So the correct answer for problem 10 is going to be A. Let's move on to problem 11. Problem 11 says, which of the following will cause the greatest increase in the boiling point of water when it's dissolved in 1 kilogram of water? The increase in the boiling point of a solvent due to the presence of a solute is given by this equation. Delta TB is equal to IKBM, where delta TB is the boiling point elevation, I is the Van Hoff factor. This is the number of particles the solute dissociates into. Kb is the proportionality constant of the solvent, and m is the molality of the solution. This is defined as moles of solute per kilogram of solvent. Now, to begin solving this problem, let's go ahead and look at each of our answer choices and first determine the Van Hoff factor and then calculate the molality for each. Then we're going to set up this expression for each of these answer choices and figure out our correct answer from that. Now, looking at our first answer choice, A, 0.4 moles of calcium sulfate. Calcium sulfate, the I value is going to be 2. It's going to dissociate into calcium cations with a 2 plus charge and sulfate anion with a 2 minus charge. So I is equal to 2 for calcium sulfate. B says 0.5 moles of iron 3 nitrate. Iron 3 nitrate, the I value is going to be equal to 4 because iron 3 nitrate is going to dissociate into 1 iron 3 plus cation and 3 nitrate anions. So the I value here is equal to 4. C is 1 mole of acetic acid. Now, acetic acid is a weak acid. It does not fully dissociate in water. Therefore, I is going to be equal to 1 for this answer choice. And then D says 1 mole of sucrose. Sucrose, this is a non-electrolyte. It does not dissociate in water. So again, for this answer choice, I is equal to 1. Now, for each of these, we can also go ahead and calculate the molality. So for answer choice A, 0.4 moles of calcium sulfate, we can calculate the molality for answer choice A by taking the number of moles, 0.4 moles, and dividing it by the kilograms of solvent. Now we have 1 kilogram of water, so it's going to be divided by 1 kilogram. This gives us a molality of 0.4. What about for answer choice B? We have 0.5 moles of iron 3 nitrate. We divide that by kilograms of solvent, which is 1, and this gives us a molality of 0.5. What about for answer choice C? We have 1 mole of acetic acid divided by 1 kilogram. This gives us a molality of 1. And for answer choice D, we have 1 mole of sucrose. We divide that by 1 kilogram, and we also get a molality of 1. Now what we can do is set up our delta TB expression so that we can figure out which of these is going to have the greatest increase in the boiling point of water. Now note, we don't have the KB value. We really don't need it because it's going to be the same for all of these option choices. KB for water is going to be the same. So really, we don't need that factor to calculate the exact delta TB. We just need a relative value so we could decide which one is going to have the greatest increase. So we can set this up as delta TB. All right. I for answer choice A is 2. All right. Multiplied by the molality, which is 0.4, and then that's multiplied by KB. All right, now we can go ahead and expand on this. 2 times 0.4 is equal to 0.8 KB. Let's do that for answer choice B. Delta TB is equal to 4 for answer choice B, that's the I value, multiplied by 0.5 KB. Now 4 times 0.5 is equal to 2, so 2 KB for answer choice B. And then for C, we have an I value of 1 and a molality of 1, and that's multiplied by KB. This gives us 1 KB. And then for answer choice D, it's going to be very similar. 1 for I, 1 for molality multiplied by KB. This gives us 1 KB. Now, the answer choice that's going to give us the greatest increase in boiling point of water is going to be the answer choice that has the largest number. All right, and the largest number here is going to be 2, and that is from answer choice B, the 0.5 mole of iron 3 nitrate. So the correct answer for 11 is B. Beautiful. Let's move on to problem 12. Problem 12 says reverse osmosis is a process that allows fresh water to be obtained by using pressure to force an impure water source through a semi-permeable membrane that only allows water molecules to pass. What is the minimum pressure that would be required to purify seawater at 25 degrees Celsius that has a total osmolarity of 1,000 milliosmoles per liter? Now, osmotic pressure is given by the following expression, where I is the Van Hoff factor. This is the number of particles the solute dissociates into. It's multiplied by M. This is the molarity of the solution. In our case, it's going to be osmolarity. And then R is our ideal gas constant, and T is temperature in Kelvin. Now, the first thing that we want to do is figure out what values we have. So temperature is equal to 25 degrees Celsius. Of course, we want to convert this to Kelvin. So we add 273, and this gives us 298 Kelvin. Now, our ideal gas constant is equal to 0.0821 liters times atmosphere over moles times Kelvin. Osmolarity, this is given to us. It's 1,000 milliosmoles per liter. And we can actually convert this to just osmoles per liter by dividing by 1,000. And that's actually going to give us 1 osmole per liter. And then I, this is the number of particles the solute dissociates into. Here, this is going to be a value of 1. For seawater, which is a mixture of salts, the osmolarity provided already accounts for the dissociation of ions, so we can just use I is equal to 1 here. So now with that, we can go ahead and plug things into our equation. We have 1 osmole per liter multiplied by 0.0812 liter times atmosphere, moles times Kelvin, over moles times Kelvin, and this is going to be multiplied by I, which is also 1, and then temperature, which is 298 Kelvin. Now here we're going to do some approximating. I'm going to approximate this to 0.08, and I'm going to approximate this to 300, and this makes this calculation super easy. This is going to be 8 times 3, 24, and let's add in those 2 zeros. And then we can't forget that we weren't multiplying by 8, we were multiplying by 0.08, so we have to move this decimal at the end of this number 2 places to the left, and our final answer is 24 atmosphere. This is our osmotic pressure. Now, looking at the answer choices, you might be stuck then between A and B, 23.5 atmosphere and 24.5. Remember that the question is asking for the minimum pressure required, which means that the correct answer choice should be slightly above the calculated pressure in order for reverse osmosis to proceed. So that means the correct answer for 12 is going to be B. Wonderful. Let's move on to 13. Problem 13 says, lead is a toxic element that can cause many symptoms, including intellectual disabilities in children. If a body of water is polluted with lead ions at 200 parts per billion, what is the concentration of lead expressed as molarity? Note that the density of water is 1 gram per milliliter and parts per billion is grams per 10 to the 9 grams of solution. Now, molarity is moles over liter. And parts per billion here, again, grams per 10 to the 9 grams of solution. So when we're talking about the water being polluted with lead ions at 200 parts per billion, we're going to say that we have 200 grams of lead 2+ per 10 to the 9 grams of water. Now, our goal is to go from here into units of molarity, moles per liter. So we're going to have to apply some conversions here to get to there. We're going to take advantage first and foremost of the density of water to go ahead and convert this grams of water into liters of water. Now we said 1 gram per milliliter, that's the density of water. We don't want milliliter, we want liter. So how can we adjust this to be equivalent? We can say that 10 to the 3 grams per 1 liter is the density of water. That's exactly equivalent to 1 gram per milliliter. So let's go ahead and apply that first conversion. 10 to the 3 grams of water over 1 liter of water. Notice grams of water cancels out. Now the next conversion we want to do is we want to convert grams of lead to moles of lead, and here we can use the molar mass. So 207.2 grams of lead per 1 mole of lead. And notice here how units of grams of lead cancel out. Now what we have essentially in the numerator then, looking at all our values in the numerator, 200 times 10 to the power 3 times 1. So our numerator is 200 times 10 to the power 3. What about our denominator? We have 10 to the power 9 multiplied by 1 multiplied by 207.2. I'm going to round that to 200 as well. So in the denominator we have 200 times 10 to the power 9. Now 200 over 200, that's just 1. And then 10 to the power 3 divided by 10 to the power 9 is just 3 minus 9. 3 minus 9 is equal to minus 6. So what we have here is 1 times 10 to the minus 6 molar. All right, so that's our molarity, 1 times 10 to the minus 6. Now we can alternatively write this as 10 times 10 to the minus 7. And the reason we want to do this is because this looks closer to what our answer choices look like. Rewriting 1 times 10 to the minus 6 as 10 times 10 to the minus 7 allows us to quickly identify that the closest answer to that is going to be answer choice B. So the correct answer for 13 is B. Let's move on to 14. Problem 14 says a saturated solution of aqueous cobalt-3 hydroxide is added to a saturated solution of aqueous thallium-3 hydroxide. What is likely to occur? And we're also given the KSP for each of these species. Now, answer choice A says both cobalt-3 hydroxide and thallium-3 hydroxide remain stable in solution. B says thallium-3 hydroxide precipitates and cobalt-3 hydroxide remains stable in solution. C says cobalt-3 hydroxide precipitates and thallium-3 hydroxide remains stable in solution. And D says both thallium-3 hydroxide and cobalt-3 hydroxide precipitate. Now this question is actually more complicated than it seems since hydroxide is involved. In aqueous solution, the concentration of hydroxide from the autoionization of water is approximately 10 to the minus 7 molar. This concentration is significantly greater than the amount of hydroxide that would be produced by the dissociation of either of these salts. Now, keeping that in mind, then the concentration of hydroxide is set by water and not by the dissociation of cobalt-3 hydroxide and thallium-3 hydroxide. That means when the two solutions are mixed, the concentration of hydroxide does not change. However, in mixing the two solutions, the concentration of the metal ions decrease as a consequence of dilution. And so as a result, both solutions would be below saturation, and that makes the correct answer for problem 14 answer choice A. Let's tackle our last and final problem for this video. Problem 15 says the following equilibrium exists when silver bromide is in solution. So silver bromide dissociates into silver cations and bromide anions, and we have the KSP value. It's equal to 5.35 times 10 to the minus 13. What is the solubility of silver bromide in a solution of 0.001 molar sodium bromide? Okay, so we already have our balanced dissociation reaction for silver bromide. From that, we can write our KSP expression. This is going to be equal to the concentration of the products raised to their stoichiometric coefficients over the concentration of the reactants raised to their stoichiometric coefficients. And remember, we do not include solids or liquids. So that means the KSP is equal to the concentration of silver cations raised to its stoichiometric coefficient multiplied by the concentration of bromide anions raised to their stoichiometric coefficient. And that's it. We do not include silver bromide in the denominator because it is a solid. So here we have our KSP expression. We know the value of this. It's equal to 5.35 times 10 to the minus 13. Now, our ultimate goal is to figure out the solubility of silver bromide in a solution that has 0.001 molar sodium bromide. So the next thing that we want to do to help us figure that out is set up an ice table. An ice table is going to help us figure out the initial concentration, the change that occurs, and then reach our equilibrium concentration. We're going to be focused on just the silver cations and the bromide anions. Now, initially, if we only had silver bromide, the initial concentration for both of these ions would be 0. But here we have 0.001 molar sodium bromide. Sodium bromide is soluble. It exists in its dissociated form in solution, which means we actually have an initial concentration for bromide that is equal to 0.001 molar. For silver cations, it's going to be equal to 0. Over time, though, silver bromide dissociates, and we're going to note that change using the variable x. Now, since there's a 1-to-1 ratio between silver cations and bromide anions, we're going to say the change is plus x for silver cations plus x for bromide anions. And so our equilibrium concentration for silver is going to be x, and for bromide, it's going to be 0.001 plus x. And that means we can go ahead and rewrite our KSP expression now. It's going to be 5.35 times 10 to the minus 13. It's going to be equal to x multiplied by 0.001 plus x. Now here, we can apply our 5% approximation rule as you always should for the MCAT problems, because otherwise you would have to use a quadratic formula, which you definitely need a calculator for, but you don't have a calculator here. So usually making these approximations is more than okay. When we do that, we say that this plus x is essentially negligible. And now what we have is 5.35 times 10 to the minus 13 is just equal to 0.001 x. And we can rewrite this in a way that makes it a little bit easier to work with this times 10 raised to an exponent. So here what we're going to write is that 5.35 times 10 to the minus 13, this is equal to 10 to the minus 3x. And now we can divide both sides by 10 to the minus 3, and x is going to be equal to 5.35 times 10 to the minus 10. We got this by doing minus 13 minus negative 3, and that gives us minus 10. So that's how we got the exponent for this number. 5.35 times 10 to the minus 10. So therefore, X, the molar solubility, is 5.35 times 10 to the minus 10. And that looks like answer choice C until you realize that the units of the answer choices are in grams per liter and not molarity. And so actually you're going to have to take your answer and multiply it by the molar mass. So we're going to take our value, 5.35 times 10 to the minus 10. All right, this is moles per liter. We're going to multiply this by the molar mass, which is 1 mole is equal to 187 grams. Now, we're going to do some approximating here to make this a little bit easier. We're going to approximate this to 5 times 10 to the minus 10. We're going to be multiplying this by 200. This gives us 1,000 multiplied by 10 to the minus 10. And now we can rewrite this in a slightly different way. Instead of 1,000, we can make this 1. And that means we can adjust this minus 10 to just minus 7. Since this is 1, 2, 3 units to the left, all right, we can add to this 3. All right, and that is how we get 1 times 10 to the minus 7 grams per liter. And that matches answer choice D. So the correct answer for problem 15 is D. And with that, we've completed our practice problem set for our solution topic. I hope that this was helpful. Let me know if you have any questions, comments, concerns down below. Other than that, good luck, happy studying, and have a beautiful, beautiful day, future doctors.